Hi students, in this session we will discuss about second order systems. And first of all, a second order system is shown in the figure, and you can see that R of S is the input and C of S is the output. And the open loop gain of the second order system is given by omega n square divided by S square plus 2 delta omega n into S. Here the order will be obtained from the power of S, that is here the power of S is 2, therefore it is a second order system. And we can see in this diagram that the feedback path has a gain of 1. So the loop gain will be obtained by the equation g of s divided by g of s into h of s plus 1. So instead of g of s, we can substitute the value omega n square divided by s square plus 2 delta omega n into s, and instead of h of s, we can substitute the value equal to 1. So that we will get the loop gain as omega n square divided by s square plus 2 delta omega n into s plus omega n square. Okay. So the input will be R of S and output is C of S. So you should remember the equation for loop gain in the case of a control system having open loop gain G of S and feedback path gain H of S, and the loop gain is equal to G of S divided by 1 plus G of S into H of S, and that equation can be applicable to all the systems which is having feedback path. So you can substitute instead of G of S and H of S different values, and so you will get the response. So that you now in this case second order system, you got the response as or loop gain or transfer function as omega n square divided by s square plus 2 delta omega ns plus omega n square. And here we can write the transfer function equation as C of s by R of s is equal to omega n square divided by s square plus 2 delta omega n into s plus omega n square, and where omega n is undamped natural frequency and that is expressed in radian per second, and also delta is the damping ratio. And we can define damping ratio as the ratio of actual damping to the critical damping, and the response C of t of second order system depends upon the value of the damping ratio. See, you can see that here the transfer function is equal to omega n square by s square plus 2 delta omega ns plus omega n square. So if you are finding out the response, you have to find the response at various damping ratios. So the delta is an important quantity, so we can analyze the system for different damping ratio values. So here the different cases are given as case 1, case 2, case 3 and case 4. First case is undamped system. In the case of undamped system, delta will be equal to 0, and second is underdamped system, and in this case delta will be is in between 0 and 1, and critically damped system has a delta value equal to 1, and overdamped system has a delta value will be greater than 1. We can analyze each and every cases differently, and before that we have the transfer function as omega n square by s square plus 2 delta omega n into s plus omega n square. In this case, characteristic equation is the denominator polynomial, that is s square plus 2 delta omega n into s plus omega n square. So the characteristic equation of the second order system is s square plus 2 delta omega n into s plus omega n square equal to 0, and it is a quadratic equation, and the roots of this equation can be given by c. Once we have an equation like as square plus bs plus c equal to 0, then what will be its solution? So solution is s1 comma s2, that is equal to minus b plus or minus root b square minus 4ac divided by 2, that is its equation, right? Here a equal to 1 and b equal to 2 delta omega n and c equal to omega n square. So we can substitute for a, b, c. So we will get the roots of this quadratic equation as s1 s2 is equal to minus 2 delta omega n plus or minus square root of 4 delta square omega n square minus 4 omega n square whole divided by 2, that is equal to minus 2 delta omega n plus or minus square root 4 omega n square can be taken outside. So square root 4 omega n square minus delta square minus 1. So in this case we can cancel the term 2 from the numerator and the denominator. So we will get minus delta omega n plus or minus omega n into square root delta square minus 1. where delta is the damping ratio, and when delta equal to 0, that is in the case of undamped system, that is delta is equal to 0, that is undamped system, and in that case the roots will be, when delta equal to 0, you can substitute the value of delta in equation 3.16, so you will get its value will be equal to plus or minus j omega n. When delta equal to 0, square root minus 1 is equal to j. So delta, when in the case of undamped system, roots are plus or minus j omega n. That means roots are purely imaginary, right? Since there is a j term, so roots are purely imaginary and the system is undamped. So that is the first case. You should remember this case and you will be using these terms. That's roots are imaginary in the case of undamped system in the coming sessions. Okay, so you should by heart it. Okay, when delta equal to 1, you can substitute the value of delta in equation 3.16. So you will get minus omega n plus or minus 0, that is omega n. That is equal to delta. When delta equal to 1, the roots s1, s2 will be equal to minus omega n. What is the nature of the roots? Roots are real, right? Roots are real and those roots are equal also. That means minus omega n is only one, s1 and s2 value will be equal to minus omega n. That means roots are real and equal and the system is critically damped. So for the critical damping condition, delta damping ratio will be equal to 1 and roots s1 quadratic equation, roots of the quadratic equation will be equal to s1 comma s2 is equal to minus omega n. That is the roots are real and equal and the system is critically damped. So and the next case is when delta greater than 1. So when we substitute the value of delta greater than 1, s1 comma s2 will be equal to minus delta omega n plus or minus omega n into square root delta square minus 1. And here the delta square minus 1 quantity will be positive. So roots are real and unequal and the system is over damped in this case. When delta value is in between 0 and 1, then roots will be minus delta omega n plus or minus square root delta square minus 1. That can be written as minus delta omega n plus or minus omega n into square root minus 1 into 1 minus delta square. Since here the value of delta will be less than 1, so in order to make it positive, we are taking minus 1 outside inside the root. So that value will be equal to minus delta omega n plus or minus omega n into square root minus 1. That will be equal to minus delta omega n plus or minus j omega n into square root 1 minus delta square. That is equal to minus delta omega n plus or minus j into omega d, where omega d is equal to omega n into square root 1 minus delta square. That means the roots are complex conjugate and the system is underdamped. So 4 cases we have analyzed. One is undamped case, next is underdamped case, next is critically damped case, this is overdamped case. And here omega d is called the damped frequency of oscillation of the system and its unit is radian per second. And next we will find out the response of the underdamped second order system for unit step input. So now we have studied about second order system and its response, and we have analyzed 4 cases, case 1, case 2, case 3 and case 4, and the nature of the roots in 4 cases. Next we will find out the response of a second order system for unit step input, and first we are analyzing the response of underdamped second order system. Okay, in the case we know that the standard form of the closed loop function of a second order system is C of s by R of s, and its value will be is equal to omega n square divided by s square plus 2 delta omega ns plus omega n square. This is the closed loop transfer function of a second order system. And for undamped system, we know that delta equal to 0, so we can substitute the value of delta. So C of s by R of s will be equal to omega n square by s square plus omega n square, and here the input is unit step, so we can write the R of t equal to 1 and R of s will be equal to 1 by s, and the response in s domain C of s will be equal to R of s into omega n square divided by s square plus omega n square, and we can substitute for R of s, that is equal to 1 by s into omega n square by s square plus omega n square, and we can find out the response by partial fraction method. So that can be written in terms of C of S will be equal to omega n square by s square plus omega n square, that will be equal to a by s plus b by s square plus omega n square. So for finding the value of a and b, we can find a by a will be equal to C of s into s at the value of s is equal to 0. Similarly, b can be found out by b will be equal to C of s into s square plus omega n square at s square is equal to minus omega n square. So first we will find out the value of a by substituting the value C of s into s, that means omega n square by s into s square plus omega n square into s and s will get cancelled. So we can substitute the value of s as 0 and we will get the value of a as 1. And the next case, b will be obtained by C of s into s square plus omega n square, where s square equal to minus omega n square is the value, or s is equal to j omega n is the value. So substituting the value, we will get b will be equal to omega n square by s into s square plus omega n square into s square plus omega n square at s is equal to j omega. So s square plus omega n square terms will be cancelled from the numerator and the denominator. So omega n square divided by j omega. So that will be equal to minus j omega n, where minus j omega n is equal to minus s. Okay, we have taken the value of s is equal to j omega n. So minus j omega n will be minus s. So we can write C of s by substituting the value of a and b. So we will get C of s is equal to a by s plus b by s square plus omega n square, that equal to 1 by s minus s divided by s square plus omega n square. We know that Laplace transform of 1 equal to 1 by s, and also Laplace transform of cos omega t equal to s by s square plus omega square, and here the Laplace transform will, inverse Laplace transform will be giving cos omega n into t. So time domain response C of t equal to L inverse of C of s, that will be equal to 1 by s, L inverse of 1 by s minus s by s square plus omega n square, that will give you 1 minus cos omega n t. That means for a step input, the second order system with the undamped second order system will give the cosine signal. That means the output will contain oscillations. So you can draw the input and output responses like this. Input is a step input, that is there is a sudden change at t equal to 0 from the amplitude value 0 to 1, and for that change the output will be oscillatory. So that means every practical system has some amount of damping, hence undamped system does not exist in practice. And here we can see that there is an undamped oscillation is obtained at the output, but it is not practically possible. So here we got the step response as a unit step response as 1 minus cos omega n into t, but in the case of step response we will get the value of a into 1 minus cos omega n into t, and here in this case undamped case output is oscillatory without damping, but such systems are practically not possible. Okay, that means output cannot follow the input from this output response. Okay, and next we will find out the response of the underdamped second order system for the step input system. And we have the standard form of closed loop transfer function as C of s by r of s is equal to omega n square by s square plus 2 delta omega n into s plus omega n square. We know that the condition for underdamped system is delta value will be in between 0 and 1, and we know the nature of the roots. That means the roots of the denominator or characteristic equation are complex conjugate, and we have familiarized it within the in this section. And the roots of the denominators are s is equal to, that we have obtained earlier, that s is equal to minus delta omega n plus or minus omega n into square root delta square minus 1. When delta value is less than 1, that is delta square is also less than 1. So 1 minus delta square is always positive. So S will be equal to minus delta omega n plus or minus omega n into square root minus 1 into 1 minus delta square, that is equal to minus delta omega n plus or minus j omega n into square root 1 minus delta square. Here omega j or square root 1 minus omega n into square root 1 minus delta square is equal to omega d, and where S is equal to roots will be equal to minus delta omega n plus or minus j omega d. This is the nature of the roots in the case of underdamped second order system, that is roots are complex conjugate. And next we want to find out the response C of S, that will be obtained by C of S is equal to R of S into omega n square divided by S square plus 2 delta omega ns plus omega n square. Once we are giving R of S is equal to unit step, then R of S will be equal to 1 by S. So C of S will be equal to omega n square divided by 1 by S into S square plus 2 delta omega ns plus omega n square. These all are simple mathematical substitutions. You can go through it by step, okay? And this equation of C of S can be solved by using partial fraction expansion. So we can write, since the denominator term contains S square plus 2ab plus C square, we can write the partial fraction expansion as a by s plus bs plus c divided by s square plus 2 delta omega ns plus omega n square. So next we want to find out the value of a, b and c. And a can be found out by the equation a will be equal to c of s into s at s is equal to 0. So we will get the value of a as 1. Similarly, for finding b and c, we can see that first of all we can cross multiply the terms on the right hand side. So we will get we know that a will be equal to 1 and we can substitute 1 instead of a. So we will get omega n square. That equation will become omega n square is equal to s square plus 2 delta omega ns plus omega n square plus bs plus c into s. Here the denominator terms will be cancelled out from left and right side, so only numerator terms will be there, and we can equate the quotient terms. We know that quotient of s square on the right side will be equal to 1 plus b, and on the left side it will be equal to 0. So b will be equal to minus 1. And equate the quotients of s. We know that the quotients of s are 2 delta omega n plus c on the right side, and on the left side there will be no such terms. So c will be equal to minus 2 delta omega n. So we can write c of s is equal to 1 by s minus, we can substitute for b and c values, that is equal to s plus 2 delta omega n divided by s square plus 2 delta omega ns plus omega n square. And here look at the denominator term. You can see that it can be changed in the form of a plus b whole square if there is a term delta square plus omega n square is there. But it is not there, so you can add delta square omega n square term there. So in order to cancel its effect, you have to subtract the same term from it also. So once you are introducing delta square omega n square to the denominator, you should cancel its effect also. So you should add and subtract delta square omega n square to the denominator, so that you will get c of s is equal to 1 by s minus s plus 2 delta omega n divided by s square plus 2 delta omega ns plus omega n square plus delta square omega n square minus delta square omega n square. You can see that I am introducing delta square omega n square terms in the denominator by adding and subtracting the same terms, so that you can write the denominator as a perfect square. So you will get 1 minus s plus 2 delta omega n divided by, you can group the terms such as s square plus 2 delta omega ns plus s square plus omega n square plus omega n square minus delta square omega n square. You can see that the first term will give you, first term is in the form of a plus b whole square. So you can write it as 1 by s minus s plus 2 delta omega n divided by s plus delta omega n whole square plus omega n square into 1 minus delta square. That is equal to 1 by s minus s plus 2 delta omega n divided s plus delta omega n square plus second term is omega d. We know that omega d will be equal to omega n square root 1 minus delta square. So again we can divide the terms in the numerator, separate the terms in the numerator as 1 by s minus s plus delta omega n divided s plus delta omega n whole square plus omega d square minus delta omega n divided by s plus delta omega n square plus omega d square. Here I am dividing the 2 delta omega n into 2 terms and each term is delta omega n. So it is in the known form, so we can apply inverse Laplace transform and we can find out the time response. Once we are taking the inverse Laplace transform on c of s, so we will get c of t, so that will be equal to 1 by s minus e raised to minus delta omega n into t cos omega dt minus delta omega n divided by omega d into e raised to minus delta omega n into t sin omega dt. Here you should know the Laplace transform of some of the terms, then only you can find out the inverse Laplace transform. So here the first term is 1 by s inverse Laplace transform is 1 and the second term is s plus delta omega n divided by s plus delta omega n whole square plus omega d whole square. It is in the form of s square plus omega d square. It is in the form of s divided by s square plus omega d square. So its inverse Laplace transform will be cos omega dt. But you know that here s is shifted to some value delta omega n. That means you should represent that shift by e raised to minus delta omega n into t. Similarly, next term is delta omega n divided by s plus divided by omega d into, here omega d and omega d are multiplied in the numerator and denominator, and denominator again contains s plus delta omega n whole square plus omega d whole square. So it is in the form of a divided by s square plus a square. So it will give rise to the term sin omega d. But here the s is shifted, so you should represent the shift as e raised to minus delta omega n into t. So you got the solutions c of t, and you can rearrange some terms and finally you will get 1 minus e raised to minus delta omega n into t divided by square root 1 minus delta square into sin omega dt plus into delta plus cos omega dt into square root 1 minus delta square. So c of t can be represented in the standard form like c of t will be equal to 1 minus e raised to minus delta omega n into t divided by 1 minus delta square into sin omega d into t into cos theta plus cos omega d t into sin theta. So that will be equal to sin a cos b plus cos a sin b. So that will be equal to sin a plus b, that is equal to 1 minus e raised to minus delta omega n into t divided by square root 1 minus delta square into sin omega dt plus theta, where theta equal to tan inverse square root 1 minus delta square divided by delta. Delta square divided by delta. So this is the equation for time response c of t. And you can find that the unit step response is equal to 1 minus e raised to minus delta omega n into t divided by square root 1 minus delta square sin omega dt plus theta. You should by heart that formula. That is unit step response in the case of underdamped second order system, and for step response a term a will be multiplied with this. Okay, so this is the case of underdamped second order system. And in this case you can find that once we give the step input, the output of such a type of system will be oscillations present at the output, but it is damped oscillations will be there. Okay, so in the case of underdamped second order system, the oscillations will be present at the output, but it will be damped oscillations. So that oscillations, that means the response oscillates before it is settling to a final value. Okay, so This is about the second order systems, and first we discussed about the general second order systems, and we will analyze it by 4 cases: case 1, case 2, case 3, case 4. In the 2 cases we have given the equations, and in the next session we will discuss the other 2 cases, that is in the case of critical damped case and also the over damped case. Okay.